Hi, this is Mrs. Kidman, and in this video, we are going to be discussing the composition of functions. Now, in one of our previous videos, we talked about operations on functions, which means we would add functions, subtract functions, multiply them, and divide them. And when we did each of these things, all we did is we took the original function and added the new one, or subtracted the new one, or multiplied it by the new one, or divided it by the new one. Now, this next one is a little bit different. What we're talking about today is composition of functions. So what that means is I'm going to put a function inside of another function, or create a new function that relies on both of these. So when we're looking at an example like this one, and we're composing these functions, notice this big difference here. A composition of functions has an open circle, as opposed to the multiplication of functions, which would have a closed circle. And when we do the composition of a function, what that means is we take our second function, whatever's listed second. So in this case, it's function g, and we're going to put it in everywhere that our variable exists in function f. So say, for example, we had the function f of x equals 2x plus 3, and g of x equals x squared plus 7. If we were asked to do the composition of this function, or the composition of f of g, what that would mean is I would want to put in function f, everywhere there's an x, I'm going to put the function g of x. So for example, with this one here, everywhere that there's an x, what I'm going to do is replace it with x squared plus 7. And then we'll add our 3 there. And so typically when we find the composition of a function, we don't just leave it at this point, but we actually expand it out so that we have the most simplified function here. So I'd multiply all of these by 2 using that distributive property, and we'd get 2x squared plus 14 plus 3, or 2x squared plus 17. So that's basically how we find the composition of a function. What we do is we take the second listed function, so in this case g, and we substitute it in everywhere the variable is in function f. So let's take a look at a couple more examples where we rewrite these composition of functions, and then we'll talk about how we can evaluate them. So let's take f of x equals 2x squared plus 8 and g of x equals x minus 4, and find both the composition of f of g of x or g of f of x. So let's take a look at this first one here. So the composition of f of g of x is the same as f having g of x everywhere that there's an x in its function. So if f of x is 2x squared plus 8, then f of g of x would be 2 times x minus 4 squared plus 8. Now again, we can multiply this out if we would like to, or we can just leave it right here, but this is what that f of g of x would be. Now what about our g of f of x? Well, this one, if we have the g composed with f of x, what that means is everywhere in function g that there is a variable, we're going to replace it with function f. So in this case, that means that we are going to have 2x squared plus 8 minus 4. And so I'm going to simplify this one out to 2x squared plus 4. So notice how these two functions are not the same. So they might be the same, they might not be the same, but in this case, we want to check both of them and assume that they're not going to be the same. In future videos, we'll talk about inverse functions, in which case when we do the composition going both ways, we actually get the same function. But if they're not inverse functions like these two, then they will not get the same thing. So let's do one more example here where we compose one of these functions. So in this case, we're going to let f of x equals 2x squared and g of x equal the square root of -1. So first we want to do f composed of g. And so that means everywhere that there's a variable in f, we're going to put the function g. So this is going to be 2. Now this is squared times the square root of x minus 1 squared. Well, this square root and this 2 will actually cancel. So this is really the same as 2 times x minus 1, or 2x minus 2. Awesome. Okay, what about g composed of f? Well, if we are looking at g composed of f here, what we're going to end up getting is everywhere in function g that there is a variable, we are going to put f of x. So we've got our function g here, but instead of putting an x, I'm going to put in that 2x squared minus 1. And so this is our other function. Again, notice how these two functions are different. Therefore, they're not inverse functions, which is something that we'll talk about later. Okay, so then the next thing we want to do is evaluate these. So when we evaluate them, notice the difference here is that inside of our question, when it asks us to find that composition of these two functions, we have a number instead of our variable. Now, when we are evaluating composite functions, or these two functions that we've composed together, what we're going to do is we kind of have two options. Option number one is we can compose first, then evaluate. So that's option number one. Or option number two is evaluate on the inside and then substitute into the outside or plug in. Substitute in the outside. So we are going to run through this problem both ways and decide which one we like the best. So the very first option is to compose the two functions. So let's do that. We've got f of g of 3. So what that means is everywhere in f of x that there's an x, we're going to put an x minus 4. So our new function, so the f of g of x, is going to be 2 times x minus 4 squared plus 8. Now we are going to evaluate it at 3. So everywhere there's an x in this function, I'm going to put a 3. So that means I've got 2 times 3 minus 4 squared plus 8. Or 2 times negative 1 squared plus 8. And negative 1 squared is 1. So really this is 2 plus 8, or it equals 10. Awesome. So that's one way to do it. It works out fantastic. Our second option is to evaluate the inside and then substitute it into the outside. So what this means is I'm going to start by just doing g of 3. And so I'm going to put a 3 into our original equation, 3 minus 4. So g of 3 equals negative 1. Now what this means is whatever value I got for g of 3, I'm going to put it into our function f of x. So now I'm going to put negative 1 into our f of x, and we get 2 times negative 1 squared plus 8, maybe. 2 times negative 1 squared plus 8. Awesome. And then this will negative 1 squared again is 1, and 2 times 1 is 2 plus 8. And this equals 10. So again, either of those options work. One of them has us compose the functions first, and then we can just solve one long problem. The other one involves substituting in twice. And so it's totally up to you which method you use. For the remainder of this video, I will probably use method number 1, compose first, then evaluate. But if you like method number 2, that is always a great option. And I would actually recommend using method number 2 if you're given something like a table or a graph. That is a better method when we don't have the actual function written out in symbolic form itself. So let's take a look at 2 more examples where we evaluate composite functions, and then you will be good to go on how to deal with the composition of functions. Let's take a look at this one here. Let f of x be x squared plus 6 and g of x be 2x minus 1. We want to find f of g of 4. So what this means is again, like I said before, I'm going to do the composition of these functions here. So when we're composing of those functions, that means that we are going to want to do we're going to want to substitute in first, and then we will use that 4 to evaluate. So let's take a look at our first option here. And we want to substitute g of x into f of x every time there's an x squared. So our composite function, or f of g of x, which is the same as f of g of x, right? These are the same way, these say the same thing. That means that I'm going to put in 2x minus 1 squared, because we have an x squared here, plus 6. Okay, so step 1, compose it. Step 2, substitute in our 4. So this means I have 2 times 4 minus 1 squared plus 6. Well, 2 times 4 is 8. So we've got 8 minus 1 squared plus 6. 8 minus 1 is 7. So we've got 7 squared plus 6. And that is 49 plus 6, which equals 54. Fantastic. Okay, so again, that method works. We can always use the other method as well if you would like. Let's take a look at one last example here where we are composing functions. And let's take a look at this one here. So let f of x equal 2x plus 8 and g of x equals 8x squared. Find f of g of 2. Okay, so what we want to do here is we are actually going to substitute g in first. So we've got 2 times 8x squared plus 8, and this is going to be that f of g of x. And now we want to evaluate f of g of 2. And so we're going to do 2 times 8 times 2 squared plus 8. And so we've got 2 times 8, 2 squared is 4. Remember, we want to do this in our order of operations. Plus 8. 8 times 4 is 32, so we've got 2 times 32. plus 8, and 2 times 32 is 64 plus 8, and 64 plus 8 is 72. So again, that is how we can evaluate that function, by composing them first and then substituting it in. Now, we have looked at a lot of examples of f of g of x, but we can actually write these functions a lot of different ways. We can do f of g of x, we can do g of f of x, we can do f of x, and g of x. So what these look like, I'm just going to compose these functions for you. When we're talking about f of g of x, those are the ones we've been doing before. So everywhere in the function f, we're going to put g of x. So this is 2 times 8x minus 1 plus 8, right? That's f of g of x. But we also could do g of f of x, meaning that everywhere in function g that there's a variable, I'm going to put f of x. So this one would be 8 times 2x plus 8 minus 1. Now we looked at those two, but we can actually compose a function with itself, which is really awesome. So in this case, we're going to compose function f with function f. So everywhere in function f that there's an x, we're going to replace it with itself. So in this case, f of x is going to be 2 times 2x plus 8 plus 8. And this g of x would be, so g of x would be 8 times 8x minus 1 minus 1. So we can actually compose these with themselves. And you may be asking yourselves, why does it matter if I'm able to compose functions? Well, when it comes to the composition of functions, that actually really comes into play when we're talking about two different events that are occurring where we need to see how they relate together. For example, sometimes we see things in the world, like in our jobs, where you might say, I get a bonus if I sell over this amount, and I also get a bonus at the end of the year that's this % of my total commission. So if I sell more than $5,000 worth of products, I get a bonus. If depending on how much I sell, I get a 2% bonus. So how much total money do I make? Well, in that case, we can use these operations or these composition of functions to determine what we have. If you have any questions, feel free to reach out, but that is the composition of functions.